we can start. So welcome to lecture 3 of the programming course. We're going to talk about a bunch of things today as usual. And first off, we will be continuing our discussion of functions from last week. So the first thing I want to say about that is that in Python, function is a data type. So for example, here's a function that does nothing, and I can ask for the type of do nothing. So in a sense, when I created that function, do nothing is now a variable, just like x equals 5, x is now a variable, and it has type function. And I could print it out. I could set it to something else even. And if I overwrite it with 5, then it's not a function anymore, so I'm not going to do that. But this may or may not be the case in other programming languages that you have worked with. So since functions are just pretty much regular objects, regular variables, we can also pass them into functions. So here's a function that I defined called evaluate function on x plus 1. And it takes 2 arguments into it. The first one, fun, is supposed to be of type function. And the second one, x, is supposed to be, say, a number. And what it does is it takes x, adds 1 to it, and then evaluates whatever function you passed in as an argument on x plus 1. So for example, I would call it like this. Evaluate function on x plus 1, square. Square is, by the way, a function that I just defined above. And 5, so it's going to take 5 plus 1. That's 6. And then it's going to square it and give me 36. Any questions about this? Yes? Tom?
Does x have to be the same name parameter above for the variable, or?
Does x have to be the same name? No, not at all. And we'll talk about that on Thursday. But this could be called y. It makes no difference. Yeah, so we'll talk more about that on Thursday. OK, so you can also write functions that return functions. You can also define functions inside of defining functions. We're not going to go into that. But I just want to say, so do nothing, recall from earlier, it's just a function of x that returns x. And let me scroll up for a minute. So in other programming languages, when you write a function like this, you have to say what type x is going to be, like x is an integer. But in Python, you just say x, and it can be any type. So this function does nothing. It really does nothing. You give it anything, and it gives it back to you. That's it. And it doesn't matter what type x is. So I could even do nothing on the function itself. So I have taken the function do nothing and given it back to myself. And now I have the function do nothing. And I could call that on 5, and it's going to give me 5. So what's happening here is that first this highlighted thing on the left is happening, which is nothing. And then I have the function, this highlighted stuff evaluates to do nothing. And then I call that on 5, and it does nothing to 5. And so I end up with the result 5. And that's just explained here. I could also call it in a different order. I could first do nothing to 5. That's going to return 5. And then I'm going to do nothing to 5 again. So they're both going to give me the same result. But in the first case, I have called the function on the function, and then called the function on integer. And the second time, I've actually called the function on the integer twice. Any questions or comments about this? The point of this is for you to know that in Python, functions are just like anything else, and you can pass them around. That's really the take-home message here. OK, next topic is anonymous functions. So we've already seen defining a function like this. Def add 1, x, return x plus 1. And we can call it like this, for example. So here's a second syntax in Python for defining a function. And I'm using it weirdly, but I'll use it less weirdly later. So here, I'm using this special keyword lambda. So if you recall from last week, I said you can't name your variable lambda because lambda is a special keyword in Python. Well, here I am using it. I'm just saying add1 equals, add1 is getting assigned the value of a function. And the function is lambda of x colon x plus 1. That the stuff between the lambda and the colon are the input arguments. So this right here is this right here. And you can also have more arguments just like in a regular function. And then the stuff on the right of colon is the stuff after return. So these two pieces of code are exactly the same. But the anonymous functions are useful in certain contexts. So first, let me just show you that. Well, how about this? Just showing you that it's a function and showing you it does what it's supposed to do. So here's some comparing of these two things. Anonymous functions can only run one line of code because it's just colon, and then everything in the function has to go to the right of colon, and whatever is there gets returned. So you can't have complicated stuff with all kinds of ifs and things like we had. It's just for a one-liner. And anonymous functions, so this whole piece of code right here, lambda x, x plus 1, that evaluates to a function. And so we can do weird stuff, or I would venture to say useful stuff with them. So here's some code that is valid Python code. The stuff on the left in the parentheses says lambda of x comma y, x plus y. So that stuff on the left is going to first evaluate to a function that adds two numbers together. And then I'm going to immediately call that function on two numbers. And I added them together, and I get 13. And the reason these are called anonymous functions is because I never actually gave that function a name. I just said what it does, and then immediately used it, and never even named it, hence anonymous functions. And where this tends to be useful is, remember our friend from a few minutes ago, just a second, Sam, evaluate function on x plus 1, then it's often the case that I have a function that is expecting another function, such as evaluate on x plus 1, and then I just evaluate, I just give it the function right in line, right there. There it is, lambda x, x to the power of 2. So there is my square function, and then 5. And so how should you think about this code? Well, first, this evaluates to a function that squares things. That gets passed in. 5 plus 1 becomes 6. And then it evaluates this function on 6 and gets 36. Sam, what was your?
Never mind.
Never mind. OK. Any questions about this? Yeah, what's your name?
Yeah.
Name?
Shivam.
Shivam.
Yeah. This 5 wasn't passed as an argument to the first function, so how does it evaluate to 36?
Right. The question was, this 5 wasn't passed as an argument to the first function, so how does it evaluate? Well, I need to scroll up and remind ourselves what this function actually does. Scrolling up, scrolling up, scrolling up. Here it is. What this thing does is it takes in a function and it calls that function on x plus 1. So the kind of parentheses that you were looking for, hey, where is this calling happening? The calling is actually happening right here. But inside of here, this fun didn't actually have a name outside of here. Inside of here, it got the name fun, and then it was called on 6. Carrie? Yes.
Can you reuse?
Louder.
Can you reuse a lambda function, or is it just a one-off?
Can you reuse a lambda function? Well, you can, and in fact here, I did this, and then I guess I could reuse it, but this is just kind of weird. Like, if you're going to give it a name anyway, you might as well just define it. But you could store it in a variable and then reuse it. The most common use case for me by far is the one I just showed you where, and you're going to see in the next couple of weeks use cases for this. Like I think Tiffany is going to talk about map, and then in R, and I'll talk about map in Python in the next course. But there's actually useful functions that take in functions, and this is really the most common pattern for using it. There was another question, I thought.
Usually
Your name again?
Victor.
Victor.
Yeah.
Yeah.
And so it's usually to only use once.
Yeah, I guess. Yeah, this is, you can do whatever you want with it. It's just part of the language, but this is the most common use for it. Yeah. It just does the same thing as def, except it's kind of worse because you can only have one line of code. It's just a convenience thing. Doesn't do anything that you couldn't do otherwise, but it just makes the code look prettier. Your name? Nikki?
Can you use the random question that was messenger, for example, instead of the value function, use another line of?
You could, yes. You could combine lambdas, but then I would say you're probably getting to readability issues at that point, even though Python would allow it. Okay, next thing, exceptions. So you may have seen stuff like this. I took this from Wikipedia. This is in some airport in, I don't know, Switzerland or something. You've probably seen humorous situations where you were in some building and one of the display screens just got you what is known as the blue screen of death. And we want to avoid that with our program. So the equivalent of this is that we're running a data analysis and something kind of weird happens that maybe isn't the end of the world, but it's just like a bit unexpected, and your whole analysis just crashes, and then you come home the next day, you come to work the next day, your code was running overnight, you're expecting a result, and instead it just says error. You know, I didn't finish for some silly reason. So the goal is that we would like our code to fail gracefully. You're never going to be able to have code that never fails, but at least if the airport screen could say, like, I don't know, out of order, or let the person know or something, but this is not what we want. So, right, we want things to fail gracefully. In Python, we can use the keywords try and except to accomplish that. So here is a line of Python code. This variable does not exist. If I run this code, then I get an error. This variable does not exist, is not defined, because I never defined it. That's totally reasonable. What I can do is put it in one of these try except blocks. So it's kind of like if else, where you have the if colon indented stuff, else colon indented stuff. It's kind of like that, except with try and except. And what's going to happen is during the try block of the code, if something goes wrong, instead of just blowing up, it is going to take you to the except block of code. So if I run this, it just says you did something bad. And why that's good is if you had a million more lines of code below this, it would just keep chugging along and running the rest of the code. And if this wasn't that big of a deal, you would maybe want it to keep going, or you would want it to fail gracefully so you could do something about this error rather than just blowing up. So that's the syntax. As I said, yeah, it tries to, it's called try because it tries to do this. And if it fails, it goes to except. You may have seen this called try catch in other programming languages. Yes, Sam?
Are there like other options for like just in PowerShell? I know there's like error action, and then you can do silently continue, like, or would you just say don't ever do that?
Are you trying to say, can you just tell it to keep going?
Yeah.
Yeah, so in Python, there is a keyword called pass. So if I didn't have anything here, it would throw a syntax error. And so in Python, there's something called pass that just means I need to have code there, otherwise it's a syntax error, but it doesn't do anything. And so if you do except pass, then it's just going to do nothing. And that's almost never the right thing to do, but it is valid Python code. Okay, Right. So above, you'll notice we got this error message from Python. Is not defined. We also got name error. So the error actually had a type, or the exception had a type. It was a name error. And I can just show you a few different ones of these. So 5 divided by 0, I get a 0 division error. And the message is division by 0. If I make a list with 3 elements in it and try to access element number 5, I get an index error because index is out of range. There is no element number 5. If I, well, this is just the same thing as the above, but more confusing. I'm defining the list and immediately calling element number 5. Same thing, same error. Here we talked about tuples being immutable. So if I make a tuple and then I try to set one of the elements of it, then I get a type error. And so there's many, many different errors in Python. As it turns out, it is actually useful that there are these categories of errors in addition to the message that it prints out on the screen, because you can do some fancy stuff with try except. So first thing is you can actually accept exception. So this capital E exception is like a thing in Python that's already defined for you. And then as EX, it basically says when it messes up, catch that exception that it was going to throw and print out to the screen and store it in the variable that I'm just calling EX. You could call it whatever you want. And I can actually print out what that thing. I actually print out maybe its type as well. Right. So this exception that would have been thrown here is a name error. We already saw from above that it was a name error. But now I'm kind of grabbing it mid-explosion and looking at it, which is actually pretty useful. So the syntax, grab the exception, again, as EX. EX is just a local variable. You could name that whatever you want. OK, so the cool thing is you can actually catch different types of errors. So you can say, try to do this. If I get a type error, do this. If I get a name error, do that. And that's useful because you might be anticipating, say, some weird things your user could do. And if this thing went wrong, you might want to have a different message than if that thing went wrong. And that's why it's actually nice that all those errors have these different categories rather than just the message, and they're all exceptions. So what's going to happen here is that I'm going to run this code. This is a name error. So this part is going to trigger, and it's going to tell me that I made a name error. Any questions about this? Alistair?
Yeah. So in the lab, I was debating between using try except or an if else to like check the index. Is there stylistically one that's better than the other? Because they both.
The question is, should I use if else or try except? I mean, they could potentially both be used to accomplish the same thing. Like, yeah, if the index is out of bounds, you could just check if it's bigger than the length. I guess it kind of depends. Yeah, I guess I don't have a good answer for that. I don't know if there's. I don't know in what contexts one would be better than the other. But yes. Oh, Serge.
Just to add to the question, maybe like if you're like having a block of code which may fail in not just one part but in different locations of the code, and you just want to like if there is an error, just skip that and do another iteration or continue further. Then that would be a good probably place to like have this try except block to be enclosed like with the whole piece of code.
Yeah, so Serge was just saying maybe you have a big thing of code, you don't know why it's failing, and that's definitely, so I kind of use this in two places. One is if you're actually trying to write high quality code, you want it to do all the right things, it needs to deal with these exceptions. The other one is kind of what Serge was saying that I use a lot, is just for debugging. Like I'm calling someone else's code, it fails, I have no idea why, and I just want to stop it at the point that it failed and then do some stuff to it, which I'll actually talk about later today. Okay, so this is the exact same code as above, but now I'm trying to do 5 divided by 0, which was a divide by 0 error, which is neither a type error nor a name error. So here I get this final except that's kind of like an else spiritually. That's like, well, it wasn't any of these other things. So but I did get an exception of some sort. So I'm just going to print you made some other sort of error.
And how do we know what is this error that we got?
Well, yeah. How do we know what error it is? So you could grab it like I showed you before and do stuff to it.
The exception is like a master exception.
Exception is, yeah, like a master exception, and all those other ones are a particular exception. I think that's fine to think about it like that, yeah. Okay, right, so you don't really want to be throwing additional errors inside of your except. Sometimes that will happen. All I'm going to say about that is you will see this at some point. During the handling of an exception, another exception occurred, and then that's just like, it's a pain, but it will happen to you. Don't despair. It just means you may have to do some serious debugging about why this happened. But honestly, this happens to me even with standard libraries sometimes. What can you do? Okay, so another thing is raise, the raise keyword in Python. So here I have a function that adds 1. We saw that before, and I'm going to add 1 to a string. That doesn't make sense. So I get an error that says you cannot add an int with a string. That's fine. And then here is my code with some checking in it that says, so this is instance is also part of the language, and you can use that. It just says, is x an instance of float? Is x a float? So if it's not a float and it's not an int, then maybe I don't want to be adding 1 to it. And so then I'm going to raise an exception and say, sorry, x must be numeric. So in other words, in addition to just writing code to catch exceptions, you can write code that intentionally causes exceptions, and that's what the raise keyword does. So if I run this code and I call it on blah, now I was the one who caused this exception to be raised, and it's printing out my personal message. And that's kind of what we were talking about before, that you may want to do that in your function so it fails in the way you want it to fail with the message you want to give and the type of exception that you want. And you'll just see a little bit of that in lab 2. Towards the very end, you have to do a bit of this exception raising. Yeah, so this is often a good idea, and when you're writing your doc strings in your documentation, it's generally good practice to describe your function's behavior, including the exceptions that it might raise. Or maybe that's like a slightly more advanced documentation practice, but it is useful for someone looking at your function to know this function might do this, it might do that, or it might raise this type of exception. Yes, what's your name?
Derek,
Derek.
would you do that description in your doc string?
Would you do that description in your doc string? That's what I'm suggesting. It's just, it's kind of like, if you're being really good about things, then you would do this, yeah. Okay, right, so this syntax also, you don't have to, I don't expect you to memorize, I just showed you like 10 different things, but one thing you can do is just call raise by itself inside the except block, and that just says raise whatever you were going to do, right? So how did you end up in this except block in the first place? Because some sort of error happened. So I'm just going to interfere, I'm going to pause it, I'm going to do my own thing, which is printing you did something bad, and then raise just means now go back about your business as if I did not catch this exception. And so that's what's going to happen. I'm going to print this thing out and then raise the original error that it was going to raise. Tiny.
Yeah. Does raise work like that only in the except or in general?
Try it out. I don't know what happens if you just... Okay, yeah. I don't think there's a reason you would want to do that. Yeah, you'd want to raise some sort of exception. Okay, any questions about try except? Serge?
Many other languages have the sort of like ensure block or finally block.
Yes.
Python has something like that?
Yes, there are some notes that I skipped over. There's a couple of bells and whistles I didn't talk about. There's a try except else and a try except finally that are kind of extra features of this paradigm. Yeah. Your name?
Ilana.
Ilana.
For the lab, we're supposed to write tests for our code, and would you want them like embedded in the function with arrays or separately?
Oh, the question is in the lab you're supposed to write tests. So for that you can just do it the way they were in lab 1. So you can just write a bunch of asserts outside the function that call the function. Okie dokie, style guides and coding style. So I've already said this a few times, but I want to hammer home the idea that just because your code works doesn't mean you're done, doesn't mean you have achieved perfection. Code really has two users. The computer, which takes your code and turns it into machine instructions and makes it actually happen, and also humans. And that human might be yourself 5 minutes later, yourself a year later, other people. So we're going to talk about this human part now, which is making your code useful for its human users, not just its machine users. So generally the word used is style, coding style, which refers to, I guess, changes that you might make to your code where it still does the same thing, but the code is different and more readable, maintainable, all that kind of stuff. So we talked about one style aspect last week, which was the dry principle, the don't repeat yourself principle. Don't have a bunch of things copy-pasted. Use a loop if it makes sense to use a loop. Write a function if it makes sense to write a function. All that kind of stuff. And we're just going to be continuing on that tack today to talk more about style and these few things we're going to talk about. So the first thing is style guides. So a style guide is basically a collection of best practices about how you should style your code. And if everyone follows the style guide, then it's just easier to read someone else's code. So there's this quote, code is read much more than it is written. And if you're working with other people and you just look at it and it's in the style you're used to, it's just less cognitive load to understand what they're doing. So we're going to follow a style called PEP8. You can click on this link and read probably more than you want to know about the Python communities, and in particular the people who came up with PEP8, their ideas about style. But here's some highlights from it. So they suggest indenting using 4 spaces, having white space around your assignment and other operators like this, but avoiding extra white space, so do this and not that. They're fine with single quotes and double quotes, but they want you to use triple double quotes and not triple single quotes. We talked about that last Tuesday. Oh wait, that's too many quotes there. Okay. The variable and function names should use underscores between words and a whole bunch of other stuff. So starting today, I guess, we're going to try to adhere as much as possible to the PEP8 style whenever we're writing Python for the rest of the MDS program. Now, that sounds like a pain. One thing that is going to help you deal with that is automatic style checking. So you can do this later, but you can install some software that will help make it a bit less painful. I've already done it. And here's how it works. So here's some bad stuff. Look at all this white space. Look at all this white space. Look at this mess. So I've installed the automatic PEP8 style checker. And somewhere, oh no, it scrolled me so far. That's sad. Here we go. Okay. And now somewhere here, I hope I have. Ugh, Where did it go? Here it is. Apply auto pep8 formatter. So I'm in this cell. I apply auto pep8 formatter, and it just formats the code to adhere to pep8, at least in the stuff it can figure out and fix automatically. So it wasn't perfect, actually, I guess. Maybe we don't really want this, but it kind of spaced things out. It added a space here, and it does a whole bunch of things beyond what I just showed you. So in the end, you might as well use something like this all the time, and it'll make it less painful for you to adhere to a pep8 style. And then it's also good because you're just going to see what it does to your code and just start to pick up the patterns of pep8 rather than trying to read and remember this 10-page document that'll be super boring. So I recommend installing this. Any questions about that? Ugh. Okay, so there's also some style things that cannot be automatically checked. So for example, it can probably check that your variable names are using underscores, but it can't check that your variable names actually make sense to a human. So spin times from lab 1 is a reasonable name. My list of thingies is not a reasonable name, but it is actually, it's separating words with underscores. It's adhering to that convention, but it's ridiculous, takes up too much space. It doesn't even describe what is in the list, even after taking up all that much space. It's just kind of a bad variable name all around. Also say like LST for list. I use that in some of my lectures, just have a little list name, but in general, you want your variable name to actually say something about what is in there, not just what type the variable is. So variable names, you should think about making them sane. Don't repeat yourself. It might be able to be automatically checked a little bit, but auto pep8 is not doing that. And then two other things, magic numbers and comments. So what is a magic number? Here is some code, a function that computes the number of labs that an MDS student attends per week. And it takes the number of, total number of labs and takes in the number of weeks. So all this function actually does is just multiplies by 4. So if you're here for 10 weeks, you do 40 labs. If you're here for 5 weeks, you do 20 labs, whatever. However, I would say this 4 here is not that great because, well, here it's kind of obvious because it's such a small function, but we don't really know where that 4 is coming from. Like, why are they multiplying by 4? In a bigger piece of code filled with 4, 7, 2.3, negative 1.5, you're going to have no clue what the person was thinking, even if it was yourself 2 months ago. I think we're all overconfident about our ability to remember what we were thinking, but usually we don't. So maybe this would be better. Maybe an optional argument. So it works the same as the other function. If you don't pass that in, it's just going to use 4, which is great. But not only can you now change the number of labs per week, but more importantly, that 4 has a name attached to it. And then by looking at it, I know what the 4 is supposed to represent. It's supposed to represent the number of labs per week. So even without writing a comment, you just kind of documented what the 4 means in code itself, not really in a comment, and that's super useful. So this would also be fine. We'll talk more about this on Thursday. How come you can access this labs per week function even though it's defined outside of the function? As I said, we'll talk about that on Thursday. But all of these things are good because it tells you what the 4 is. So that 4 is called a magic number. We want to avoid them. They make the code hard to read. And here's my real fear. Compute the number of labs an MDS student attends per week. Compute the number of wheels in a bunch of cars. I know this is a really silly example, but I'm making a point here. OK, you have 10 cars. That means you have 40 wheels because every car has 4 wheels. And then one day, MDS is going to change the program to 3 labs per week. And someone's just going to come in a bit low on coffee and say, oh, 4, change that to 3, 4, change that to 3. And then suddenly the car thing is totally messed up. Or maybe they'll even do a search and replace, or who knows. But in a giant piece of code, you see a 4 here, you see a 4 there. You might think they're the same 4. And if you give those not only a variable, but also a name, that'll avoid this disaster over here. Questions about this? Ryan.
I actually have a question about the mentions for the variable name. Like in the statistics, like people use the case for a random variable, it doesn't conform to.
Yeah, okay. So Ryan's question is, sometimes you might want to use like an uppercase letter because of the math that you're working on. I'm totally fine with that. So like, it's often the case that like a matrix would be a capital letter and a vector would be lower. Yeah, that's all good. But I mean, all these rules can be broken with your better judgment, but it's just like in the absence of a reason, do it this way. Any other questions? Okay. Last thing, comments. So comments are important. Docstrings cover what a function does. As we talked about last time, a docstring should not talk about the innards of the function, but comments totally can. So comments are there to just explain. Like, in a way, the most beautiful code is one that doesn't need any comments, but that's not always realistic. So sometimes you need comments to explain what's been going on here. Again, PEP 8 has guidelines on how comments should look. But in addition to how they should look, they should also make sense. So you remember, hopefully, the RandomWalker from Lab 1. And here's a comment that you might do. So here, I'm explaining how it works. Generates a random number between 0 and 1, then go in a direction based on if the number's in these intervals, blah, blah, blah. That's, to me, a reasonable comment, because if it's not there and someone's never seen this before, they might say, what's going on here? And then they read that and they say, oh, I totally get it. And maybe the code isn't completely self-explanatory, especially since I asked you to do it in this particular way. And maybe even the PEP 8 kind of says, we don't really like inline comments, meaning comments on the same line as code. But you can do it sometimes, and maybe this is a reasonable use case. Or maybe, you can do it here, or whatever. It doesn't matter to me. So that's all good. Here's some bad comments. So initialize chords spelled wrong. Loop t times, that's just obvious. Like for I in range t is completely self-explanatory. That is just as clear to the reader as the English, because that's just such a common thing in Python. You're labeling 3 out of the 4 directions with no capitalization. Print the location again. Pretty clear what that code is doing without a comment. In Python, yeah, come on. Like you can assume the reader of the code has used Python before. By the way, I made this up. I didn't take this from someone's lab. That would be mean. I just came up with this. I came up with this myself. Opinions are purely my own. But yeah, you can just start to get a sense of what are reasonable comments and what are unreasonable comments. And there aren't hard and fast rules, but you kind of get a sense over time of how to do it. Okay, let's move on. So the next thing is the Python debugger. That is a Python package called PDB, which stands for Python debugger. And the lead in here is, OK, my Python code doesn't work. What do I do? So again, here's the RandomWalker. Oh, yeah, I renamed it to adhere to PEP 8. RandomWalker, so here it is again. I think this is a working. Oh, this is not a working version of the code, so it looks not that terrible. But when you look at it and you run it enough times, you'll realize that it actually always goes left, meaning the x coordinate always goes negative, never goes positive. So I can run it a few times, and you can just see, which is a little disappointing because the code looked kind of OK. So what do I do here? How do you debug your code? Well, one thing you can do is just add a bunch of print statements, which is kind of like the simplest way to debug stuff. I just want to know, well, what is going on here? So what was this random number that got generated? And you know what? I'm going right. So maybe I want to print in here just to make sure all that stuff is working. Then I run it again. I look at the random numbers. They look kind of okay. Now, here's something a bit fishy. Why is it going? Oh, that's because I just messed up. Here we go. I'm going left. Yes. Okay. So we can start printing things out. Personally, I'm not finding this all that illuminating at this moment, but often printing out stuff is useful when debugging because you can just see, well, what was this variable equal to at this particular point in time? So the alternative to this is PDB. We import it. We'll talk more about importing on Thursday, but you put import PDB at the very top of your file. We'll just say that for now. And then once you import it, there's this pdb.setTrace, which, at least for me personally, is the only aspect of PDB I've ever used. So you stick it in there, and then you run your code. And when it gets to pdb.setTrace, it just pauses and says, hey, here we are at this point. Now do whatever you want. You can print stuff out. You can even modify, make new variables that didn't exist before. You could even mess with the code, although you probably don't want to do that. And then there's just a whole bunch of features that, frankly, I don't use, but you probably should use, that allows you not just to stop, but to step through the code one line at a time and execute exactly what's going to happen. Execute the next line of code, and then stop it again and see what happened. Execute the next line of code. And so I put a link to the PDB docs, but there's like N goes to the next line, and C, and I don't remember exactly what they all do, but there's some very nice conveniences to just step through the code. To me, even just the ability to pause is massively useful. And I don't know if this is like that great. I guess it is fine. I actually often use this together with try except. If something's driving me crazy, I just do try the thing that's messing up, except pdb.setTrace, and then it just means when it blows up, stop there, and then I can start inspecting things and seeing what, because sometimes you have like a big loop and only on the 19th time does the error go, and you can't just put a set trace there or it's going to stop the first time. Anyway, I just do that try except thing even if it's not that elegant. So let's take a 5-minute break and resume at 11:40. We are back. So the remainder of today's class, we will be talking about NumPy. NumPy is perhaps the most useful to you Python package. Certain programming languages like MATLAB or R were designed with computation at the forefront. Those languages were created for doing computation. However, Python is a general purpose programming language that is used for scripting and server web development stuff and bajillions of different things. And then we're going to use Python for computation even though it does a bunch of other things. Therefore, some of the features we need are not actually native to Python the way you're going to see in the next couple of weeks. Some of these things are native to R. They're just part of the language. In Python, NumPy, which is like the backbone of everything related to computation, is not a default part of the language. We actually have to bring it in. And on Thursday, we'll talk about importing and what that means. But it's not a core part of the language in quite the same way. So here we go, import NumPy. So NumPy is a Python package that gives us this array data type that we're basically going to be using a lot of the time to store our data. The second piece of this is pandas, which Tom is going to talk to you about in the data wrangling course next block. Why is it still importing? Goodness. That's weird.
Probably because you have PDB.
Oh, thank you, Serge. How do I even get out of here in the... Okay, that was good enough. Thank you. Great. Good. Thank you very much. Okay, so I've imported NumPy. So we saw lists before, and on the surface, NumPy arrays are kind of like lists in that they can store multiple things in them. So here's a NumPy array, and the type is called numpy.ndArray. That stands for n-dimensional. We'll talk about the multi-dimensional aspect in a few minutes. But here it is. It's storing a bunch of numbers, but it's very different from a list. So first of all, a list can store things of different types in them. A NumPy array is more like a traditional array from Java or whatever. It can just store a bunch of things of the same type. Tom, right?
Yep.
Yeah.
Just a quick question before we move on. When you do you always have to import packages, and where are they being installed?
Yeah, we'll talk about that on Thursday.
Okay.
We'll have a whole section about importing packages. So I cannot really make a NumPy array of things of different types. It's actually going to turn one into a string, which is, I don't know, I think that's a bit insane. I would rather it just threw an error there. But anyways, we don't really want to do that. We typically are just using NumPy for numerical data. Typically floats in particular is the most common form for our data. So how do we create these things? An easy way to create NumPy arrays is with the zeros function. So everything with NumPy is going to be np dot something, and we'll talk about that more on Thursday, but it's going to be np dot something. So np dot zeros, for those of you who's used MATLAB before, by the way, this is basically based off of MATLAB, so the syntax is very similar. np dot zeros 10 just creates an array with a bunch of zeros in it of the size. So with lists, you typically start with an empty list, and then you keep adding things to it. With NumPy, you typically decide in advance how big it's going to be, initialize it full of, say, zeros, for example, and then start filling it in. And that's what I expect you to do for Lab 2. So immediately at the beginning of Lab 2, you need to start building a NumPy array. Do something like this. You know how big it's going to be in the lab, so create it full of zeros with this function, and then start putting stuff in it. And I'll show you how to do that, but it turns out to be the exact same as with lists. So here's, there's also np.ones. Of course, you could just make it full of zeros and then add 1 to it, but it's just a common thing that people want ones, so they made this function. A range is quite similar to the regular Python range. So it gives me from 1 inclusive to 5 exclusive, but it's actually giving me a NumPy array, unlike the Python default range. And you can do all the stepping, just like the regular Python range. You can do other kind of steps and all that. Another common thing is linspace. Again, it's named after a MATLAB function. So this says, this gives me 20 equally spaced points between 1 and 5. So that's just kind of comment that you want a grid from this to that, and you want some reasonable number, like 20, and then the spacing is like some weird thing, and it just calculates it for you. If you had 21 points, then they would be nicely spaced, but there you have it. Okay, so just convenience things. There's nothing really deep about this. In Lab 1, you use the Python default random library to generate random numbers. NumPy has its own more sophisticated random number generator capabilities. And I don't know if you've done it yet in 5.5.1, but in R, you can generate numbers from distributions with tons of functions in R. And again, those are all built into R. In R, you're not importing some library and then using that to generate. It's just directly built into R. Whereas in Python, we need to use NumPy, so you can generate from a Gaussian distribution or a binomial distribution or whatever using numpy.random. Okay, so here's 5 random numbers uniformly distributed in, from 0 to 1. Now where it starts to get way, way, way more convenient than lists is these element-wise operations. So here's my NumPy array with 4 ones. By the way, the 1 dot, the dot is just telling you that they're floats. That's just how it shows you. It's like 1.0, basically. So these are floats, not integers. And now I can just do x plus 1, which would not work with the list, and it adds 1 to all the things. Again, it's like a math-driven part of the language. So from linear algebra, you could take a vector, add 1 to it, and what you mean is add 1 to every element, and that's what's happening here. So I could subtract things. This is a bunch of 1s minus a bunch of 2s. Gives me a bunch of negative 1s. If x and y were different lengths here, it would give me an error. But since they're the same length, when you say x minus y, it just assumes you mean the first thing in x minus the first thing in y, the second thing in x minus the second thing in y, etc., etc. So maybe that would actually be more, oh well. Okay, so I can do element-wise equals equals. Is the first thing in x equal to the first thing in y? No. Is the second thing in x equal to the second thing in y? No. I can do element-wise multiplication, element-wise exponentiation, element-wise division, all these kinds of things. So very convenient for mathematical computational stuff, which we will be doing a lot of, not surprisingly. There's also array equal. That just checks, is the entire array x equal to the entire array? Because you saw earlier I did equals equals. That was an element-wise one. So if you want to check if they're just, are they the same overall, then you use array equal. Okay, questions or comments? Okay. Array shapes. So array shapes is where it gets interesting. So x from before, we can ask its shape. So the dot shape gives you back a tuple. That comma thing, it's just, oh boy. If you want a list with one thing in it, aside tuples with one element. So if you can make a list with one element like that, but if you do parentheses 1, it just thinks it's like the math parentheses 1, and it just gives you back the number 1. It's like you're taking the number 1 and doing math to it in parentheses, but there's actually no math. So if you want to make a tuple with one thing in it, you put the comma there. And that's now a tuple. Okay, so that was just an aside to say that x.shape is a tuple with one element in it, which is 4, and 4 because there's 4 things in it. I could also ask for the length of x, which is 4. And that's not that interesting, but here's where it gets interesting. So you could have a list of lists. We saw a list of lists in lab 1. And in NumPy, you can actually make a proper two-dimensional array. So note the syntax here. You are actually passing a tuple, the tuple 3, 6, to the zeros function. And the 3, 6 are the dimensions of the array you're trying to create. And here's the result. So it is a 3 by 6 thing. So it has 18 elements. And all the conventions come from linear algebra again. So the first number is the number of rows, and the second number, the 6, is the number of columns. And you can also, you can transpose it so that it's the other way, and all those kinds of things. So when I ask for the shape is 3, 6, and that makes sense because I told it to make an array with 3, 6. So it means the first dimension is of size 3, and the second dimension is of size 6. And I can also say size. That's the total number of elements. That's the 18 I was talking about before. And I can also ask for the number of dimensions, which is 2. So this is basically length of x.shape. X.shape is 3, 6. It's a 3 by 6 array. So x.shape is a tuple with 2 numbers in it, 3 and 6. So the length of that tuple is 2. There are 2 dimensions, two-dimensional array. The earlier one was just a one-dimensional array, the x with just a bunch of zeros in it. The shape of it was just a tuple with the number 4 in it, and so that has 1 dimension. Questions? Yes, Furkan.
So with this NumPy, for the 2D like say arrays or 3D arrays, do always follow the tuple?
Yeah. So to create one of these things, you need a tuple in here, except for the 1D array, when you could just call zeros of 4 and be done with it.
And this is true for all the NumPy functions that are there, right?
Yeah. But very well. Now it's a little annoying. Unfortunately, no, actually. So annoying things. So actually, if you want to make random numbers, you don't put in a tuple. Don't blame me, I didn't come up with this. But you just kind of get used to it. Yeah. You can always look up the documentation. Yeah. Any other question? Yeah, I already forgot your name. Sorry. Nikki. How can you put the list in order?
In the like the 3x6 order.
How do I put what in the 3 by 6?
Instead of zeros, you want something else.
Yeah, I'll get to that. Yeah, I'll get to how to put stuff other than zeros in it soon. Yeah, what's your name? Sukriti, yeah.
When you're making arrays, the number that is coming up are floats, right?
Yes.
And that's by default.
Yes, everything's floats by default. You can make them ints. I don't really do this very often, but now they're integers. You can also do, yeah, there are ways to make them other types, but like 90-something, you usually want them to be floats, yeah. Again, you don't need to memorize all of this. You're going to look it up when you need it, when the time comes. Okay, dimension and length. So this is just like some frustrations about the English language and the word dimension and the word length. Those words are extremely broken because they have 2 meanings. So here is the problem. In a linear algebra class type thing, you talk about a vector, like in the RandomWalker. That was a 2D random walk because the person was walking around in 2D. There was an x and y coordinate, right? But if you made a NumPy array to store that location, RandomWalker location, we say it starts at 0, 0. Or let's do this. Starts at 0, 0. That was a 2-dimensional random walk. We had x and y. They weren't walking 3-dimensional. They weren't going into the sky, right? So in our human English language, we say that's 2-dimensional, but in like programming, that variable is a 1-dimensional array because a 2-dimensional array is the stuff we looked at before with rows and columns. This is extremely confusing, problematic, annoying thing that you have to be very careful about. Just this meaning of the word dimension. So this is a 1-dimensional array. That is its type, programming-wise. But in human terms, it is representing a position in 2-dimensional space. You just need to keep that in mind. And then yeah, okay, that we just talked about that, so that's fine. But then the word length is pretty bad too, because you could say, well, instead of calling this, now I have 5 things in it. Instead of calling this a 5-dimensional vector, because we just said that's messed up, let's just say it's an array of length 5. But even that is highly problematic. It is not wrong to say that the length of it is 5, but in linear algebra, the length of a vector has this mean in terms of like Euclidean norm thing where it's like you sum up the squares and then you square root it. So if I had a vector from here to here, we would take its length, like Pythagorean theorem kind of thing. So the word length and the word dimension are basically just fundamentally broken for our purposes in that they both mean two things that are used in very similar contexts. So I don't have a solution, just wanted to raise awareness that if something is confusing you, it could be this. Any questions about that? Yeah, and as we get to the classes with more like vectors and matrices and stuff later in the program, that word dimension is going to get thrown around a lot in more than it has been so far. Okay, so you can also have a three-dimensional array. Here it is. Let's actually look at it. So Python cannot really print out things like coming out of the screen to show you a three-dimensional array, right? So it's just printing, I don't know what to call those anymore, rows, columns, and something else, right? But it's just printing them out like this. So the first dimension, here's part 1 at the top, and then there's a space, and here's part 2 at the bottom. And then there's 3 of this second dimension and 4 of this third dimension. The size is 2 times 3 times 4. There's 24 floats sitting in this three-dimensional array. And you could even have 4-dimensional arrays, 5-dimensional arrays. Yeah, and actually, yeah, we'll get to indexing and slicing very soon, but just want to say one more thing. This is a very sad thing. A 1D array in NumPy, so np.1's 5, it's just a one-dimensional array. Its size is 5. Its ndim is 1. Its shape is a tuple with 5 in it. But you can also make a 1 by 5 array. What is 1 by 5? I mean, it's the same thing. And it looks pretty much the same when you print it out, except with some extra brackets. Both of them have 5 ones in them, and they behave very similarly in like many contexts, but they are not the same Python object. And in some contexts, your code is going to break because your function was expecting one of these, and you got the other one, and it's just a huge pain. I don't really know what else to say, but you need to know that this could be happening to you. And then the third thing is you could have a 5 by 1 array. And that I'm not so upset about. Like in linear algebra, there's like a row vector and a column vector, and they actually behave differently in math. So, okay, yeah, I guess it's fine. But then that third one, the one at the very top that is one-dimensional, really throws me off. So this is just like kind of boring. There's nothing really going on here, but you just have to know about this because there's actually 3 shapes of just you have 5 things in your array. 5 by nothing, 5 by 1, and 1 by 5. Right, and none of them are equal to each other. Oh yeah, also just the element-wise thing. So here I can add x and y even though they are those slightly different shapes. You'll have to wait until Tom teaches you the data wrangling course to understand why this happens, which is potentially bizarre behavior if you're not expecting it. So we'll stay tuned. Okay, now what you've been waiting for. How do I get stuff out and put stuff in? So we'll just make an array with some integers in it. So in fact, there's not that much to say because the indexing and slicing of 1D NumPy arrays is absolutely identical in every way to the indexing and slicing of lists, tuples, and strings that we talked about last week. So this gets you element number 3, which is actually the 4th element. This is the same as lists. That's the same as lists. That's the same as lists. Same as lists. This -1 gets you the last element. That's the same as lists. We talked about that. I think we talked about -2 gets you the second last element. Some weird, more advanced stuff like counting backwards. I just had that in the example last week where I was reversing strings and I had the : -1. So this is the same as list. It says go from 5 to 0, counting backwards in steps of -1. it's all exactly the same. For 2D arrays, here's some random integers. So this is one of those numpy.random functions that is kind of nice. It just gets me random integers between 0 and 9. And I just told it the size. I wanted a 4x6 array of those random integers. Just super convenient to have functions like this. And here's how we index them. So x34 says, get me the element in row 3, column 4. So row 0, 1, 2, 3, column 0, 1, 2, 3, 4. That should give me a 7. That should give me this 7 right here. 0, 1, 2, 3 for the row, 0, 1, 2, 3, 4 for the column. This next thing also works, but I do not really like this as much. Do this. So in the next course, I will show you some contexts where those two things are different, and it's pretty much universally better to do the first one, although in this context, they both get you the thing in the third row and fourth column. Okay, x3. So what is x3 going to do? Well, that's weird because it's a two-dimensional array, but I'm only giving it one index. So what this is going to do is actually just going to get me the third row. So just like a list of lists, you could think of this 2D NumPy array as an array of arrays. And so x3 is just saying, get me the third row. And in fact, that's actually why this code over here works. Because x3 gets me, as you can see, the third row. So this was evaluating to the third row, and then it was giving me a 1D NumPy array that was the third row, and then I was getting the fourth element in it, and that's why that worked. So that's potentially pretty useful. It's also why the length of x returns 4, because it's actually saying, well, x is just a thing with 4 rows in it. That's, I would say, like, just confusing. And you really, 99% of the time, what you care about is the shape, which gives you the full picture of what's going on. Just taking the length of a 2D array is weird. Questions? What's your name?
Luke.
Luke.
So the indexing in this case is start from 0?
Yes, the indexing is always going to start from 0 in Python. Yeah. Okay, so here's some more stuff. So x comma 3 got you the third row. How do I get the third column? So you use colon to say, give me everything in that dimension. So x colon comma 2 says, give me everything vertically and just column number 2 horizontally. And this gets me column. I'm saying column number 2, not second column, because it's really the third column. And you can just see, here it is, 2830 is coming out here, 2830. And you can just do weird stuff. All that weirdness that you can do with one-dimensional arrays, like slicing with colons, you can do here. So this should get me rows 2 and onward, and columns 0, 1, and 2, and it should give me like a sub-matrix of the original thing. At this point, I'm just kind of spamming syntax at you. There's too much of this to process in real time, but I just want you to see it, and you'll probably want to refer back to it later. And I showed you the transposing. OK, I never actually said how to set things, which probably would have been highly relevant. So I can set things exactly the way I set things in lists. So here we go. I just set element 1, 1. And if you have a 1D array, you just say like x square bracket 0 equals 5 or whatever. So setting things is also the same as lists. These are mutable. Yeah, just like lists. OK, Boolean indexing. Well, actually, I just want to make a, just because it's very relevant for your lab. I just want to be very explicit that you can set things like that. And you can create a loop with an index like I going from 0 to 5, and then you can set things using that index. So the first time in the loop it sets the first thing, the second time in the loop it sets the second thing, and that's what you're going to have to do in the first part of your lab. Okay, Boolean indexing. So here is a NumPy array, a one-dimensional NumPy array with 10 things in it. We saw this from before. Element-wise operations, meaning I can add 1, it adds 1 to the whole thing. I can also do element-wise greater than. I didn't show you that before, but here it is. That's funny. Ollie is the... Anyway, okay. So what I did is x greater than 0.5. And so for every element in x that was greater than 0.5, it put in true. And for every one that was less than 0.5, it was false. So it's again element-wise. Is the first one greater than 0.5, second one greater than 0.5? Tiny, let me, I'm a bit short on time here, so I just want to try to get through this. Here's what's called Boolean indexing. So inside the index, I have x greater than 0.5, which means I am indexing x. What is x greater than 0.5? Well, we just saw it. It is another NumPy array full of Booleans, true, false, 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 true. And this is a fancy and highly useful way of indexing NumPy arrays where it just, all the elements in x corresponding to true get indexed. So what this line of code actually does very succinctly is set all elements greater than 0.5 to be equal to 0.5. So now you have all the things that were less than 0.5 just kind of left alone, but anything that was greater than 0.5 got set to 0.5. And of course you could do a loop or whatever, but this is just so convenient and nice, super useful, and that's called Boolean indexing. Okay, Tanya, I do have time for your question.
The syntax of x plus 1, it doesn't actually change x, it just shows it.
Yes. The syntax, so x plus 1 does not change x. That's just in the same way that if I had a number and I did x plus 1, it also does not change x. So that's all the same with NumPy arrays. Yeah, it just it gives you back a new NumPy array of the same size as x where everything is bigger by 1. Any other questions? Okay, then we'll wrap up here, and I will see you next Thursday.